is really the answer to that I don't want to admit. Yeah, the unfortunate truth. There's just like a little version of me today. Mini me. There's an old reference. You guys even know that reference? Okay. Mini me? Yeah. Yeah. Okay. You guys were like toddlers at the time that movie came out. You shouldn't have been watching that. Maybe not you.
Thank you. Let me tell you, that miniature version might be good for mobile phones watching.
Yeah, that's true. 3 pixels will be my face. Okay. So, Lecture 5.3, Vibration Isolation Table Analysis. So this is actually a fully worked out example, and it's in the notes. I did it this way because I wanted you guys to have just like the whole thing in all of its gory detail there, and nobody would be like transcribing anything wrong or whatever. So also it's very long, so we couldn't really work through this problem in class. If we worked out all the details. But what we'll do is I'll walk through this solution and just talk about like what we're doing at each stage and why we're doing it. And we're putting together material from the last semester and this semester. We're going to do a linear graph model, a state space model. We're going to find the equilibrium state for the system given us a certain constant input. We're going to find a transfer function model, an input-output differential equation model, and then we're going to solve that differential equation, and we'll comment on the system's stability at the end. So we're going to do like a lot of the steps that we've learned thus far in system dynamics analysis, even starting last semester with the linear graph modeling and state space modeling. So we're going to do all of it. We're going to do that for a problem, a vibration isolation table problem that is actually a model that comes up a lot for mechanical engineers. And it'll come up especially when you guys are in your senior class, vibrations. Okay? That class is it gives you a glimpse of sort of the power of this sort of system dynamic modeling approach, and it gives you a way of designing for vibration isolation, which is a big issue. So say you have a motor that's on some chassis, and it's almost inevitably you're going to have a bunch of vibrations coming from the motor, or if it's an engine, you have even more vibrations coming from that. And a lot of times those vibrations can cause a lot of issues in other equipment if it gets, like if your engine or motor is bolted to something that's stiff, and it'll transmit these acoustic waves through your plant or your room or whatever it is you have it in. And some of the side effects of that aren't that big a deal. Like you hear like rattling somewhere, which is kind of annoying, but that's not a big deal oftentimes. Other times it's more of an issue where you can't get a proper measurement from your accelerometer on some other device because you've got all of this noise coming through the ground, through the floor. So you often will need to isolate either maybe the instrument that needs to be isolated from the floor, or maybe the motor can be isolated from the environment so that it doesn't transmit all of that to the environment. So that's the type of thing you would want to do with a vibration isolation table. But this sort of analysis, this mass sitting on top of a spring and a damper analysis that we're going to use as a model for our vibration isolation table, that arises in a lot of situations. So this can also be used for a car model, for instance. If you're going to model the suspension system of a vehicle, you can model it as being a spring mass damper system. And the velocity input here would be maybe from the profile of the road. Maybe you're going to go over a bump or So we're going to do a step input. So that would be maybe modeling a sudden step in the terrain, and what would the how would the car react? Like, is the car going to end up bouncing a bunch of times afterwards? If you've ever been in a car that has poor suspension, you can you can tell it's a little dangerous because you feel yourself like not really having good control right after you hit a bump. So that's an issue that you see come up even in like vehicle dynamics. So this model is very common to use in a lot of cases, and a vibration isolation table would be just one example of them, of the type of case you would see this in. So given this model, so I drew the schematic. So we already interpreted this thing as being a mass spring damper system. So I didn't start with the table, but I already took us to this point. And I give some of the parameters, so the mass, the spring, and the damper values, okay? And I want to go through this entire analysis of all of the different aspects that I described. So we'll start out, and we'll do the linear graph and state space models. This should all be familiar to you from the mechatronics course, how to go through this. A linear mechanical system. We draw our linear graph where we have a velocity source connected to a mass node via a spring and a damper element in parallel, right? So that's important. And we can identify from this linear graph that the state variables are going to be the velocity across the mass and the force through the spring. You can go through and do your primary and secondary variables if you like. That's probably a good step. I kind of glossed on that a little bit here because it just took up a lot of space. But then we get to the state variables. The input vector is just containing one element, which is the input velocity. And then we'll take the output to be the velocity of the mass. So that's typically like if you're thinking of isolating whatever's on the tabletop from vibrations coming through the floor, then you would take the velocity of the mass to be a velocity of the tabletop, or the equipment on the tabletop to be the output. In other words, the variable in which we're interested. So the elemental equations are as follows. We have three elements, the mass, spring, and the damper. So we write out their elemental equations. The first one is just Newton's second law, right? F equals ma. The second one is the time derivative of Hooke's law, which is we differentiate F equals kx, x being the displacement of the spring from equilibrium. And B is a damper, and so it has a force that is proportional to the velocity across it. So those are our elemental equations. Then we have the continuity and compatibility equations. So for each branch, which is each passive element in the normal tree, we will have a continuity equation. So we could draw a contour something like this. That's the contour I used. And we know that all of the force leaving this node, all of the through variable leaving this node, must equal all of the through variable going into this contour. And we have the force on the mass being equal to the force in the spring plus the force in the damper. So Fm equals Fk plus Fb. And then for each link, each element that's not in the normal tree, we have a compatibility equation, which is the loop equation, right? So the first loop is that Vk, so thinking vector addition wise, Vk is equal to Vs minus Vm, right? And then similarly, Vb is equal to Vs minus Vm. So the same right-hand side. So those are our continuity and compatibility equations. Finally, we can eliminate the variables in those equations that are not state variables or inputs. and we can come up with the state space model of 5, 2. Okay, so second order system, 2 by 2 A matrix. This is our standard form, and pretty straightforward. So that wasn't too bad. The state space modeling aspect was, I think everybody's pretty much on board with that process here. And then the next thing we wanted to look into, so we've got the linear graph model and the state space model. Let's review what we're trying to find in this problem. So linear graph model, state space model. So check and check. 3, the equilibrium state, x naught for the unit step input. So for any constant input, we can find what the equilibrium state will be. We showed that we derived what that equilibrium state would be in the previous lecture. And in order to use this formula, so this is the formula that we want to use. In order to use that formula, we need to know what A inverse is. It's only valid if A is invertible, so you can try inverting A, and if it has an inverse, then you are good to go. So we'll compute it, and it does have an inverse. There it is. And I just used the, there's a footnote in the next section that says which appendix in Rowell and Wormley the discussion of matrix inverses lies. And it has 1 by 1 and 2 by 2 example in there. So this is in there. So you can just flip these two, and you can change the sign on these other two in the diagonal, divide by the determinant of the matrix, which is the K over M. So, great. That's our A inverse. And so it has an inverse after all. Let's compute the equilibrium state. We just plug that A matrix in, or the A inverse matrix in that we just computed. We have the B matrix we plug in, and then the input U is 1 for all time greater than or equal to 0. So we just do the matrix vector multiplication, and then the trivial, this is a 1 by 1 matrix you can treat as just being a scalar, right? So a scalar multiplication of a vector. And all you have left in the end is just the vector 1 and 0. So remembering that we chose our state vector to be Vm and Fk, then we know that Vm, the velocity of the mass, needs to be 1 meter per second for a unit step input equilibrium, and the force in the spring should be 0. So what is that? Let's interpret that for a moment. If we want equilibrium, what we need is if Vs is going 1 meter per second, then Vm has to be going 1 meter per second for there to be equilibrium. And that sounds like an equilibrium state, right? You've got two ends of, so like that would be the table top is moving up at 1 meter per second, and the floor is moving up at 1 meter per second. So you don't have any acceleration, it's just a constant velocity that's happening. So we have equilibrium at that state. So 1, 0. Great. Now let's turn to the transfer function model. So the transfer function, the output over the input in the Laplace domain, Vm over Vs, will be used as a bridge to the input-output differential equation. So that's mainly what we're using it for right now. The transfer function can be found from the usual formula from lecture 3.7, so you can review that if you want to find the derivation of this equation. So it's C si minus A inverse B plus D. So first let's compute Si minus A inverse. So I actually show some of the steps here. So I'm like actually going through some of these in detail. So if you're having a little bit of trouble remembering your matrix arithmetic, then it's good to go through this. And then the inverse as well. And then we plug in this SI minus A inverse term that we compute right here in this formula of 5,9. And we compute the entire expression, which gives us 511C. Ooh, this one. Great. And that's a transfer function. It's a polynomial in S in the numerator and a polynomial in S in the denominator, where S is the Laplace transform S. Okay? So now we're ready. So we laid the bridge down, so now we can just walk across it to get our differential equation. The input-output differential equation can be found from the reverse of the procedure of lecture 3.7 of going from a differential equation to a transfer function. It's easy enough to go to a transfer function from a differential equation. It's just by inspection. So if you look at, so I actually showed a few steps, even though we could just look at this and write down the differential equation by inspection. I show a little bit of how to go about that by saying, okay, the transfer function is the ratio of Vm over Vs. If I moved this denominator to the left-hand side and I move this denominator to the right-hand side, we get this next step here. And then all we have to remember is that in the time domain, S is the differentiator operator, right? So S becomes a time derivative. So instead of having the Laplace transform of Vm, we have Vm that's in the time domain, little vm. And instead of having an S squared, we're going to have a second time derivative of Vm. Instead of having an S, we're going to have a first time derivative of Vm. And instead of having a Vm that's a Laplace transform, we'll have a Vm that's time domain. And all of the coefficients come down. And similarly on the right-hand side, we have a time derivative of the input as well that arises. Yes?
Why is the Vm small after
Yeah.
and the Vs is large?
So we're using the convention that big Vm, so capital letters are Laplace domain variables, and lowercase letters are time domain. So this direction would be Laplace, and this direction would be inverse Laplace. So that's the convention we're using. We're not completely consistent though, because we use capital letters for inputs usually, and for some of the variables, we'll even use capital letters. Like when we get to fluid systems, we're going to use capital P for pressure and capital Q for flow rate. So in time domain and in Laplace. So either you have to know from the context which domain you're working in, or you should explicitly put in the functional argument of S or of T. Yeah?
So because the Vm, I understand why that one switches, but I don't understand why the Vs is different and does not become a lowercase.
Yeah, and so that the problem with that is that what we have here is Vs of S, so our input is already capitalized in the time domain. So we have Vs of S, and then we have down here Vs of T. I probably should explicitly put it in there. The trouble is when you have a lot of them, it just like makes your expression a lot longer, and I think it makes it more opaque. So it's harder to see what the expression's saying. So it's implicit there that all of the Vs's are functions of time in this last expression, and all of the Vs's up here are functions of the Laplace variable S.
So it would be lowercase, but we're using a capital Vs as the variable already.
That's right. So the time domain one, we already used it. So when I defined Vs up here, I already used capital. I could go to lowercase. If I knew I was going to spend a lot of time in the Laplace domain in this problem, I could maybe say, okay, instead of doing that, I'll call this VS. That's probably a good way to go with it. But yeah, this is one of those situations where we have a lot of sort of clashing notational conventions that happen. And like you try using a capital for Laplace and try using a lowercase for time domain, but in certain cases, capitalization kind of denotes something else too. So yeah, it's why computers have a really hard time understanding what the hell we're talking about with natural language, because we do this sort of thing all the time, where we just, given context, we have conflicting conventions, and we just kind of make stuff work. And like this will, like, people will get it. It'll be fine. Computers don't like that very much. That's part of why AI has been a lot slower coming with natural language processing, because of how we're apt to do that. If we just had like a completely rational way of symbolizing stuff, computers would be able to do it a lot better. But we have this very strange, broken way of symbolizing things. So, okay, so now we're ready to look at the step response. So we've got the input-output differential equation. The step response is found using superposition and the derivative property of LTI systems. So this is the stuff we just learned, right? This is the stuff that we learned in the preceding, well, this is from 5.1, actually, superposition and the derivative property. So the forcing function is the right-hand side of the input-output differential equation, right? It's the side that has the input terms on it. So the forcing function is f of t, is typically what we'll call it. It is this expression. It's composed of two terms, one of which has a derivative of the input vs. So one of them has vs, so the right one has vs, the left one has vs dot, the time derivative of vs. This is actually a somewhat complicated little expression here, because we have a time derivative of a step input, which is actually the Dirac delta function. So you have like a Dirac delta input, and we have a step input, and we have scalings of them, and they're added together, and they're both going into this system. So that's a pretty complicated forcing function. So rather than attempting to solve the entire problem at once with this like big, massive forcing function, we choose to find the response for a forcing function f of t equals just the unit step, okay? And so that is the unit step response. And then use superposition and the derivative property of LTI systems to calculate the composite response. So that's our goal, is we're going to say, okay, we know that if we find the unit step response to the system, we know how to construct the part of the solution over here, because if you scale the input by k over m, according to superposition, you scale the output by k over m. We also know the solution to this problem. If we know the solution for vs, we know the output for vs, then we know that if we take the derivative of that output, we'll get what the output would be if we put in the derivative of vs. So we put in vs, and we got, say, vm1. And if we put in vs dot, and we got vs2, we know that vs2 is just vs1 dot, just the time derivative of the first one. So that's the logic we're going to use, and then we can also use superposition together to scale that response. So that's how we're going to construct a solution to this relatively complicated forcing function using our superposition principle and the derivative property. So that's our goal. So to find the unit step response, it's still a bit of work, right? We got to go through, find the characteristic equation. And we solve for the roots of the characteristic equation, which are complex, right? They have non-zero complex conjugate values. And if we're going to think about this in terms of the complex plane, where this is the real part and this is the imaginary part, we've got one of them showing up here and one of them showing up here, right? That's where they are in the complex plane. So the system, we're expecting to have a damped sinusoidal step response. Because damped because they're in the left half plane, right? So those roots have negative real parts, so we expect them to die down to 0. And oscillatory because we have a non-zero imaginary parts. Okay, so I decided what I wanted to do is I didn't want to solve this out. I could have done it with the numbers in there the whole time, but I thought it would be better if I did it for whatever those numbers were, just like complex roots. And we'll just say that lambda 1 and lambda 2 are sigma plus or minus j omega, where sigma is the real part and omega is the imaginary part. So if we do that, we know that our homogeneous solution is, of course, the sum of a constant times e to the lambda 1t plus a constant times e to the lambda 2t. There is no multiplicity for either root, right, because they're both distinct roots. So we don't have to worry about the t factor in there. And in this form, C1 and C2 are complex, which is because the lambdas are complex, so C1 and C2 are complex. It's true, but we also don't tend to like this form as much. It's not as intuitive to us. So what we'll do is we're gonna transform this using some identities, using specifically Euler's identity, and then just mixing up with some algebra. We could come up with this expression, which does not look at all simpler. What we see is this exponential term that comes out front, e to the real part t, which is why that real part's got to be negative, right? If that real part's not negative, then we're going to have an exponential that grows, or at least is constant if it's 0. So then we've got these constants combined together to give us a cosine and a sine term at the same frequency. So we know that's actually a single sinusoid with a phase offset, right? So C1 and C2 are just some complex constants that we don't know what they are. So we're just going to say now we're going to have new constants, C3 and C4, and the C3 and C4 constants are actually going to be real, and that's convenient. So we prefer this form, and you may have seen this, like when you did your differential equations class, you may have said, oh, for a second order system, we assume the homogeneous solution is of this form. Well, that's great, but that's not generally applicable beyond a very specific complex conjugate root pair. So that's why this expression is the more general expression. But in this case of complex conjugate roots for a second order system, it's kind of nice to have it in this form of 5/16. So that's the form that we'll use. A decaying exponential, hopefully, well, it is in this case because sigma is negative, and a sinusoid. So that's what we've got. So it's a decaying sinusoid. A nice aspect is that C3 and C4 are real. Okay, so we've got our homogeneous solution. Now we need our particular solution. So it can be found by assuming a solution that is of the form VMP, the particular solution, being a constant for all time greater than 0. Remember that we're using the method of undetermined coefficients, and we have a table that tells us, okay, if you have a constant input, if you want the particular solution, you should assume that it's going to be a constant output. Assume that's your solution. And then how we determine if it is a solution is we try plugging in that solution and see if it works. Okay? So we plug it in to our differential equation, and then we try to solve for what the undetermined coefficients are. In this case, we only have one undetermined coefficient. It's k. So we solve a capital K. So we solve for capital K. In other words, we determine it. So we are determining the undetermined coefficient, and we find that it's just equal to m over little k, or the mass over the spring constant. So if we could find a solution for it, that means there must be one that exists, and therefore it is a solution. And therefore the general solution is the sum of the homogeneous and particular solutions that we derived, given in 518b. So this leaves the specific solution to be found applying the initial conditions, which we didn't have them given in the problem. So we'll assume them to be 0. That's a pretty good assumption usually if it's not given in the problem. Before we do so, however, we need the time derivative of the step response. So notice I'm calling this VM step, because this is not the solution to the entire differential equation, right? I'm just finding the solution where f of t, I'm setting f of t equal to 1. So I'm calling that solution VM step. And in order to plug this in to find the general solution, my coefficients C3 and C4, from my homogeneous solution, I need to take the time derivative because it shows up in the differential equation. So you do that, and I get that C3 and C4 are as given there. So applying the initial conditions, I get C3 and C4. Okay, so now I have my general solution for the step response, and I'll write it as a single sinusoid where I've got an amplitude A1, a decaying exponential, a cosine term with a frequency omega, and a phase offset psi 1, and then the particular solution term is there at the end. So then we have used this formula A. So in the appendix of these notes, A to 11 is an equation, or is, I think it's a subsection of that appendix that gives the equation for combining two sinusoids with the same argument into a single sinusoid with a phase shift. So we've used that formula several times, but it's a useful one to have. So we've got now our step response for the system, unit step response. And now we're going to use superposition and the derivative property to derive the specific solution in the case that we actually have, right? So recall that the actual forcing function is a linear combination of the input and its time derivative. Therefore, it is expedient to rewrite the time derivative of the unit step response. So we just take the time derivative of 521, so time derivative of that expression, and it gives us this expression. So you take the time derivative and you end up with this expression here. The reason that it comes out like that is that we've got the product rule that comes in, right? So the first time you take a derivative, you take it of the exponential, and then the next derivative is going to be of the cosine. So you end up with a cosine and a sine term again, and once again you want to combine them using the same formula that allows us to combine sinusoids. Great. So we're combining those sinusoids. We're loving it. It's great. We have our VM step dot, and now we're ready to apply superposition. So remember that right now we have we put in a forcing function f of t equals 1, and it gave us VM step, right? Now what we're going to do is we're going to put in f of t, the forcing function, that we actually have, which is b over m vs dot plus k over m times vs. That's our actual forcing function. I guess what I should have done here is, instead of putting f of t equals 1, really it was vs, and then we plugged in vs equals 1. So that was our forcing function we did for vm step, where we said vs is 1. And this time we're going to put in that forcing function, and it's going to give us vm. But instead of having to go back to the drawing board, we can construct the solution for Vm using the form of this forcing function and the knowledge of what happens when we put in Vs. And so we do that here. And what you see is that Vm is equal to b over m times Vm step dot, which used the principle of superposition and the derivative property in the same step. So what it did was it said, okay, if I know that the solution is Vm step when I put in Vs, then I know when I put in Vs dot, I should get out Vm step dot. And I know if I put in a factor scaling the input, that factor shows up on the output. So I used the derivative property, and then I used superposition. And then with the second term, you only need superposition. When I put in Vs equals 1 into the system, I got out Vm step. But now I'm putting in k over m times 1, and I should get k over m times Vm step out. So that's that was just superposition. We didn't need the derivative property there. The superposition just tells us if you scale the input by k over m, scale the output by k over m. And that's what we did. So then I just plug it in, and I get this expression here. And it's probably worth plotting this response. And so I did so. And I used MATLAB to do it. And I think I'm going to use MATLAB almost exclusively in this class. I might use a little bit of Mathematica, but this is the MATLAB code. I just define what my parameters are, and then I define the secondary parameters based on them, so the lambda, sigma, omega, the constants that I define. And then I just define a function that is just my solution using an anonymous function in MATLAB, so I didn't have to use a separate function file. It's kind of nice. And then I just plot it over the first few seconds. I create a time array vector, and I open up a figure. I plot the vector versus the function evaluated at the times in the vector. And the rest of it's just labeling and saving the figure. If you try to execute this last bit, you do need to get the hgsave function from the MathWorks website, but you just don't have to save it, and you can just skip that part. And this is what comes out. Well, if you pretty it up a little, which is what I did for these notes. But so this is the response. So if you put in a unit step velocity to this system, you're gonna have this response that happens like this, where it's going to shoot up. So the velocity of the mass is going to shoot up and end up going faster than 1 meter per second for a little bit, and then it's going to oscillate and go slower and then faster. So you're going to see this sudden jump in the velocity that of the bottom of the table, and then you're going to see the top of the table shoot up and then sort of bounce a little bit, and settle down finally to a velocity of 1 meter per second, which we knew because we already calculated what x naught is, the equilibrium value, right? We knew that that's where it would end up from our equilibrium analysis from above. Okay. Finally, we can talk about stability. We've learned what we need already in order to analyze the system's stability, because the roots of the characteristic equation were this, which clearly all have negative real parts. So there are only two roots, so you just need to check those two roots to make sure that their real parts are negative, and they both are, so the negative 1.875 in both cases. So the system is therefore asymptotically stable. So this sort of analysis is, I would say, totally within your reach. You guys can totally do this. It's definitely a long analysis, right? I mean, like with this, it's 7 pages typed, and I tucked in a lot of the corners. So like if you're working this out on paper, it would be probably 14 pages, okay? It's quite a bit of work. But I do expect you guys to be able to do that at this point. I don't expect you to be able to do it in a 50-minute exam necessarily, all of those steps. That would be too much, right? That would be just take too much time. But I expect you to be able to do it if you were given an assignment at home to be able to do that. The power of this is pretty great. So we aren't really seeing it at this point, but you know, you're not going to design a vibration isolation table and then really worry about what happens if you put in a unit step input to it. It was just an easy input for us to see all of the stuff that we wanted to see. What I wanted to do is put in a sinusoidal input to it, because that would have been more interesting to see in terms of the vibration analysis. So if you had vibrations coming through the floor, they would look sinusoidal, right? Not like a step. And if they looked sinusoidal, let's think about what would be different. Not a lot, but one thing that's different is our particular solution. Instead of being super easy, just a constant, that was our particular solution. The particular solution took this much space. Wasn't bad at all. If it had been sinusoidal, it would have been messy, right? And we would have had another sinusoidal term showing up out here at actually a different frequency, at the forcing frequency. So there's like a whole other thing that comes in, and it gets even more complicated. So you're seeing the like explosion of like you can use this analytic technique, but the complexity increases more and more when you add new forms of inputs and when you add complexity to your system. And it's starting to break down. It's not breaking down in the sense that we can't do it. It's breaking down in the sense that it's cumbersome, this solution technique. And we're going to learn some new solution techniques moving forward that are going to help us kind of come up with more shortcuts to answers and focus on different aspects that we care about. So, yeah. I think that's all I've got for you. So I'll see you guys not Monday, Martin Luther King Jr. Day, and then I'll see you guys on Wednesday.